Welcome again to Math Essential Vector Calculus. Today we are with the first serious topic, the gradient, which defines the direction and rate of change in scalar fields. Let's have a fast recap from 1D calculus. Normally, if we have a function of the variable x and would like to take the derivative is defined at the rate of change or the slope. For example, at a point x naught, if we make the tangent here, the slope of this tangent line will simply be derivative. So what is the gradient? So in multidimensional, the gradient is just the multi-dimensional derivative, and simply the gradient projects onto any direction to give the rate of change along that direction. And mathematically we can write that the derivative of a function in the direction of a will equal to the gradient of this function multiplied by the unit vector in this direction. So in short, we can say the gradient magnitude also is equal to the rate of change per unit distance in that direction. So let's learn how to calculate the gradient. So for a given scalar function in the dimension u1, u2, u3, the gradient will be the multiplication of nabla by the function f, and nabla we have already defined before, and just by applying nab make differentiation in each direction of the function f, partial f by partial u1, partial f by partial u2, and partial f by partial u3. And of course you need to take care of the scaling factor in each direction. And we need to note that this only applies to orthogonal coordinate systems. If we think the gradient is a system with an input scalar field, the output is a vector field. If you recall from our previous videos, we have the 3D coordinate system which we have learned: Cartesian, cylindrical, spherical, and by applying scaling factor which we have here, we can get the dedicated gradient equation for each system. Scaling factor are just ones in case of Cartesian, so you'll just find the unit vector multiplied by the derivative in the specified direction. In case of cylindrical coordinate, rho, phi, and z, only the phi component will have a scaling factor which is not equal to 1. Here it equal to rho. In case of the spherical coordinate, we have two angles, theta and phi, so we are sure that there is some scaling factor. So in case of theta, the scaling factor is r, and in case of phi, the scaling factor is r sine theta. So from engineering perspective, we have a lot of application regardless of your field of study, such as in electromagnetic. We have the gradient of the potential, and this actually define one important vector field, which is the electric field. So electric field is simply equal to minus gradient of phi. And in another field of study, such as fluid dynamic, we have the pressure gradient, and this defines the force because f vector f is equal to minus nabla p. And in thermodynamic also we have the temperature gradient, which defines the heat flux q equal to minus k nabla t, where k is the thermal conductivity. Now let's have a physical example from thermodynamic to understand the gradient. It is a localized heat spot, so we have a heat spot in the middle here, and this is just a metal plate. And what will happen if you make a localized heat spot? You will have heating in the middle, which will raise the temperature, and gradually when you move towards the outside, your temperature will decrease. So here, of course, this is the farthest point, so it will have minimum temperature, and of course in the center you will have maximum temperature. And this actually is defined by the function here t. If we take the gradient of this one to understand how heat follows, this t by dx in I direction plus partial t by partial y in the j direction. Once you do this one, only have the exponent term here. If you make the differentiation, you will have 2x. Of course, t here I take common because also you will have 2y, and at the same time you will have 1 over a square I take in the outside, and t naught was just a constant, and exponent, when you differentiate, you will keep it again the same exponent. Now if you try to understand what is going on, how the gradient moves, just assume y is equal to 0, then you will find that your gradient is just, if you are coming from the negative x-axis, it will point towards the origin. And if you come again from the positive x-axis, you will have the same 0 and vary y. So if you are coming from a negative y-axis, you are pointing in this direction. And if you are coming from positive y-axis, you are pointing in this direction. And if you have arbitrary value of x and y, now you will find yourself make again pointing to the point of maximum here. So what is going on here is that your the gradient is pointing to the heat spot which was causing the heating. And as we said in the previous slide, your heat flux or Q is just equal to negative this gradient, so your heat will follow in the opposite direction. To wrap up, we have learned today the gradient tells us how nature wants to move. So we have a movement from high to low of a scalar field, and the gradient converts a scalar field to a vector field. Think about a system. We have a gradient here, we have input a scalar field, and we have output as vector field. And in the following video we'll discuss about the divergence, which help to detect sources and things in vector fields. Thank you.